So today we are very happy to have Louis with us for the first episode of this season. I've known Louis for quite some time now, and I'm so happy to introduce him. Louis is an assistant professor at the University of Nottingham, specializing in human-centric robotics. His research focuses on developing intelligent robotic systems that can safely and effectively collaborate with humans in various environments. His interdisciplinary work spans geometric methods for manipulation and control, complex object manipulation, cooperative manipulation systems, safe physical human-robot interaction, and both implicit and explicit human-robot communication. Additional research interests include biomechanics-aware assistive robotics and applications of control theory and geometric algebra in robotic systems. Professor Figueredo leads a dynamic research group dedicated to solving real-world robotic challenges through collaborative and interdisciplinary approaches. He firmly believes that meaningful advances in the field require cross-disciplinary cooperation and perspective, and the important part is along with a steady supply of coffee. So at this point, I will stop sharing, and Louis, the stage is yours.
So my talk is about getting comfortable around humans, like getting physical human-robot collaboration to work. And this is a personal view. It comes from my experience with robotics from early age. This is my childhood think about robotics. I always like to show it's how I was excited about it, and Jetsons growing up, and Star Wars, and viewing robotics as these amazing creatures. And starting my PhD in robotics, super excited, way younger than now, and with more sleep, but definitely super excited about it. Didn't even know that Baxter it's the Baxter, so excited to work with the Baxter as well. And this is several years later with my PhD students. They're recording this to show to their family in China that this work with really was working, and that was about 4 a.m. So they brought me to from my office and was showing, and they have a demo set up with beers at 4 a.m. I was just too tired to not stop laughing about this old situation. And this was just exactly to show. So it was here they're talking about the quaternions, so it makes me laugh. And the idea of the collision avoidance, imitation learning, and didn't work. So this is basically to show how challenging human by interaction is, and just having a little bit of a rounding about why that's so challenging. I added a few additional slides, and I will go quick on that because a lot of people already know that about how we get to the human-robot interaction part, especially how you get to the physical part, and what are the challenges that we have in robotics. So robotics, and of course, a lot of people know here about it, but robotics started on the 50s. It's the baby science, so it's the newest science, and we are growing still. So in the 60s, we had the Unimate, which is this amazing robot that we have a lot of activities with it. And in the 60s, we had the boom of AI and the boom of, I believe, in robotics will solve everything. That's where we start the Jetsons. That's where we have Shaky from Stanford, this amazing piece of work, which was doing so many works that we are already doing today. So here is Shaky doing path planning, collision avoidance, even recovery. And there is a very nice jazz playing behind that I'm not going to show because challenge with the shade, the sharing. But even you can say even processing commands as a sort of a natural language, early ages, and dealing with uncertainties of the world, and is able to solve it. So if you haven't seen, I recommend everyone to see. It's an amazing piece of work from the time. But the point is that brought a lot of confidence around the world that AI and robotics will solve everything, which you might think there is some parallel what is happening to today. And in the 70s, we have the AI boom, or the AI winter. That basically that didn't really realize that was promised. And that's always very challenging very tricky to overpromise. So robotics went a little bit back, went to industry, went to directly applications where it could be apply, and you see the financial and the impact output very straightforward. So that's industry, and a lot of focus on the mechanical design. So there is a lot of work on building mechanics. That's where we got the first really humanoids working on factory. In the 80s, we see those in large scale in manufacturing. That's the first time that we see assembly lines with massive amount of robots. And at the same time, with that boom that we had, that research that we had on mechanics, led us to the first humanoid designs, to the first legged robotics, highlighting a little bit the Honda, but there was a lot of work going on. And a little bit the start of computer vision as well. So in the 90s, that started work on computer vision, led us to improve teleoperation. The mechanics also led us to have robust mobile systems, and that led us to go to Mars with NASA, the Sawyer, the rover, and the computer vision and the mobile capabilities behind it. And also the development of the first humanoids with Honda as well, highlighting they were doing amazing work for the 80s and the 90s on that. So that's always, you can see that there is always this gap between 10 years when they started working, when the community starts working on it, and when you get really great outputs, there is this time for evolving the technology. And from that, the 90s, we started with the development that has been done. We have the Boston Dynamics, which started in the 90s as well, with the Big Dog in the early 2000s. We have the now in the RoboCup in the 2000s as well. And we have this new trend of robotics. We have drones first time being deployed in non-military actions. So being allowed to use for civilians. We have the first mainly used surgical robotics going into industry. And we have the development of compliant robots with DLR leading the work and really allowing to have more physical and close interaction between robots and people. All this development, we jump again 10 years, and then we have the Topper Challenge, we have the Boston Dynamics with the Atlas. So we have really advanced humanoid designs. It's still not being able to do a lot of tasks in the world, which we all know it's very challenging, but really pushing towards the field, and a lot of investment from the Topper as well, which you will see the result nowadays, 10 years after. At the same time, the work that DLR was doing, develop compliant manipulators, we see the boom of manipulator companies and compliant manipulator companies 10 years later. Then we see the KUKA Lightwave with the Franca, the Universal, so the cobot booms. And you see also nowadays, oh, I skipped one slide, I apologize for that. So we see nowadays the development of natural language processing and the output that we get from from that early age works. So coming back to nowadays, and I'm gonna update about what is the status from my view and the challenge regarding to human-robot collaboration is mainly because of that history that we have. So here, the history, you can see the works on robotics and the works on human-robot interaction and physical human-robot interaction. And you can see clearly the trend. Robotics has been a long time. We have about 30K works on robotics per year. And this is a Google search with those keywords that are highlighted. And you see that physical human-robot interaction, physical human-robot collaboration, it just started. It's basically 10 years, 15 years ago. So now is the time that things are really kicking in. You see the exponential growth in research, and it's gonna go, it's still gonna grow. So more people working on the topic, more people involved in this research, more people involved in the community work on it, we are gonna see great advances in the coming years. So now, coming back, just to give this introduction about the topic, I'm just going to talk a lot about my view about how we build robots that can interactly close and physically with people. Building reliable robots, mainly, that's the critical part. So first, don't drop gears on people and mostly on your supervisor. Please don't. Don't ask ChatGPT. Improve my drawing skills doesn't help much, but having a layered approach, it does. So that's my perspective. This is what I'm going to show a little bit of different works on the topic. So my view is that to build reliable robotics that work close to people, we have to have this layered approach where very high-level abstract AI-based, model-free-based works on natural language processing, communication, VLMs should be embedded in different layers of safety and understanding of the world, understanding of the physics, understanding of the robot capabilities, primitives, which finally should be embedded in safe manipulation. So talk a little bit about how we go from there. I will start with safety. So first, and naturally, if you talk about physical human-robot collaboration, we are talking about human safety. And safety comes on the collision part as the most critical aspect. When you have a collision with humans, that's is basically there are different aspects, different points, different phases of the collision. And the only aspect that we can manipulate, that we can control, is the pre-collision aspect, basically adapting ourselves, and the post-collision impact. The point of the impact is where the energy is transmitted, there is nothing you can do. It's the instantaneous transmission of the information. So it's basically the energy and the modeling of the formation, which model do we have. So when you come to the pre-collision aspect, I'll go very quick. So basically here we have the control. We have the control information about the energy that is transmitted and the point where this energy is transmitted. So basically, if you have like a sharp object or if you have a blunt object, and what is the reflected mass and the velocity that at the point of the contact. And this is what you can control. So having a comprehensive view on that, you can control not just the velocity, which is what has been done historically, just reduce the speed, which is what you do with your car. If you're having a collision, the first thing you do is just brake to reduce the speed of the collision. But a manipulator is not a car. So you can also manipulate the reflected and affected mass that you have at the effector point on the collision. So it's like a boxer that manipulates its posture to achieve higher damage and higher affected mass while transmitting the contact. We want to do the other way around. We wanted postures that reduce this transmission, reduce the reflected mass at the point of contact, such that we can be faster and safer. I won't go too much on that. I'll talk a little bit more about the post-collision impact. So basically what happens in these scenarios where unintentionally we have the collision and the robot needs to have safe behaviors behind it. So my approach here was first with Jonathan to design a taxonomy, which is a PhD student at Munich. So it was to design a taxonomy of potential cases that you have from the literature, potential cases of collision between human robots, design what the scenarios that they can happen, design what the reactions based on the literature that the robot can take. And that goes all the way from stopping, which the only certified reactive reflex engine allowed, all the way to impedance, force adaptation, motion adaptation, and so on. So here is basically a few studies that we did. We did more than 1,000, 2,000 experiments in these different scenarios with control equipment to contact the forces and the reaction and the time that it takes. So contacting some of the safety features that we assume that are relevant in contact. So here you can see the stop reflex. Here we have active retraction behaviors that we tell exactly how much the Cartesian space or the joint space the robot should retract from the original trajectory. And backtrackability behaviors from admittance to 0G, super 0G, and so on. And here you can see them in slow motion just for understanding the difference between them, right? We also analyze secondary collisions. So basically what happens if you collide some at some point, and you can see in the top figure, and I hope you can see my mouse, where you collided to the top part, and then because of that collision, you generate a secondary collision in the bottom part, which is the measure equipment. Also, if you have something that is on the sideways, what kind of torques you generate during the contact. So we designed a few experiments to evaluate what are the behaviors that we have and what the reflex can cause as the secondary motion. And we talked to biomechanics experts. We did some in vivo experiment as well, and we analyze a few of the safety features that we should be attended in secondary collisions after the first collision, the post-collision stage. And this is what we call safety features. And the safety features, the safety factors, design what are safe for those different scenarios. So we can talk to an expert and design what are the safety factors for one specific scenario that is possible in our taxonomy, which the blue spider graph here. And you can see it's the same for all of them because it's one specific scenario. And from our previous experiments, we know what are the safety factors from all the possible reflex agents, from the stop, admittance, zero-G, super zero-G, the hybrid, where you basically have the admittance, it's basically impedance with constrained rotation and so on. And you can see that some of them will be safe and some of them won't. And the idea is that once you have that information, you don't choose the ones that are unsafe, and you only select the ones that you know through experiments that are safe to be used. So here it's a quick example. So after the first collision, we go in our taxonomy. I'll just speed it up so we can go a little bit quicker. So after our first collision, we go on a taxonomy and we evaluate. And here stopping criteria is safe because we don't have any chance of constrained contacts. So you go on, but now the stop criteria will cause clamping. Would cause a very dangerous position. So the best behavior here is a zero-G kind of behavior. Now we have a secondary contact and stopping continue being safe. So we take that the stopping, which the only one certified. That's the main reason why. And now again, naturally stop is not safe. But also having a zero-G behavior here will cause the objects to fly around. So here we have either admittance, where we constrain the orientation of the object that we are carrying, or hybrid impedance with constrained orientation. So this is very important to make sure that while we interact with people, we have this kind of safety behaviors in place. But none of those are useful if your robot doesn't behave as you expect. So here we bring some of the robotic safety behavior. So basically the certified controller part of it. And here you can see a few of them. So the joint space constraints, and this is basically like a variation of control barrier functions, but on the time and space. So Cartesian constraints and what happens if you don't have it, and in the manipulability space. So what happens if the manipulability is not on, and then you reach singularities and the safety conditions where you are allowed to manipulate the robot. And with those, so with those, and this is just to illustrate a little bit the concept behind that on how we build the constraints. It's basically sign distance functions that we can use to build that kind of constraints. I won't go just because of time, but I will show what we can do with this kind of behaviors. And if there is any question, we can go back later. But I will just go a little bit on what we can do with this kind of certified behavior for manipulation. So here we model a liquid transportation using the concept from more than 300 years ago of the Moroccan T-trade device or Turkish T-trade device, and using the modern version of it, the Spionot device. And we model the same system, the same dynamics in the manipulator, which required quite guarantee behavior, guarantee constraint of the motion, and you're able to have this kind of behavior, where the robot emulates the dynamics of the spherical pendulum, which is the Moroccan anti-trade device, and with all our conditions guarantee manipulation. And we go a little bit further because it's just simulating a behavior spherical pendulum, so it can run in real time. So we devised basically a teleoperation system. And the teleoperation system has a major challenge for these scenarios because you cannot just break the system when it's reaching a joint limit or a boundary limit, because at that point, you might be tilting the cup. So we need to have this time bounded so we know when you're going to reach the boundaries. And as you're going to reach the boundaries, before we reach them, we have to match the two dynamics and reduce the speeds that we have. So kind of control barrier functions that we define what are the speeds, the input from the teleoperation device. So even if you're given a command, as you reach the boundaries, you're not allowed to satisfy that velocities. And then we run again on our equations for the spherical pendulum, and we execute in the robot. And with that, we did some lab experiments, which is always quite scary. So in the bottom is in the Iros in Japan. Really nice, really scared. Was the first time we were presenting for a lot of robots is trying to break the system. And we asked literally people for breaking the system. So teleoperating with the cell phone here. And on the top right, this is in Automatica Fair, trading fair in Munich, with a lot of people playing around. So we gave an export controller and asked people to break the system while we are playing with the robot. We also implemented some admittance behavior where you can push the robot like that. And the robot also has the same kind of control behavior. And having kids play around, it's always super scary, but it survived. We survived. That's the most important, and it was a very good experience. But just to add on top of that, the requirements that we have to have safety in the robot is human safety, having certified behaviors for manipulators, and having reactive behaviors. So here is basically me trying to break the robot, where the robot it's not grasping the ball, so it's just making contact points on the ball. While I'm moving one of the arms, the other arm has to adapt itself reactively on real time such that it doesn't drop the ball. So this is just a play to show the reactive behaviors that robots needs to have to guarantee safety as well. So here, the only way to have this kind of performance on real time is to reduce dimensionality, especially if you have a binomial manipulator. If you try to control everything, you're going to reach limits. You're going to reach scenarios that your robot just cannot do it. But the task doesn't require you to do all those things. So a task that requires you to make contact points in a ball is basically distance related. Even the orientation are not relevant at this point. So if you reduce the dimensionality that you have, so you define the task in terms of the primitives and define what you need actually to perform that task, that makes it much easier for a system to perform it. For instance, if you're doing collision avoidance, you don't need to follow perfectly the trajectory that you have. But if you follow a funnel, that gives a little bit of flexibility for the manipulator to play around and to get away from limits. So here you can see some of those advanced contacts, so the advanced applications that we have in these scenarios. We've put agent planning and playing around with different reflex, different real-time reactive planners that allow us to do that, and allowing also physical contact to be integrated in the planning stage. Also to manipulate different geometries and the manipulator tools, for instance, all this with the geometric information behind it. So this is the core aspect. This is the safety and reactive real-time engine that needs to be running underneath the robot. On top of that, then you can have, for instance, imitation learning. You can have user-guided demonstrations that are embedded in planning stages, which this is exactly the same algorithm that was running when they dropped the beer on me. But now it's running with a proper information about the endpoint position where it needs to deliver the cup and is able to solve the task. you're able to extend the same principle to different manipulators having the same task because the task is defined in the task space. You can use the same information, the same demonstration for a bimanual system to include obstacles in the scene and play around with different scenarios. And because all of that is geometric based, we can also integrate a little bit more complex scenarios where you have the objects moving while you are executing the task. You have multiple demonstrations, and that allow us to do our funnel-based approach, where different kind of behaviors is allowed, and we explore exactly that to do whole body avoidance, to have the behavior where the manipulator is able to execute a task, even if the task is changed online. So this is the kind of behavior that exploring the geometry and integrating with the user guided in, as I mentioned, the layered approach allow us to do. We're also exploring the embodiment of the robots, and this I just want to show the concept of flipped solutions. So basically having, whenever you have endpoints where you're doing IK search, for instance, you can have these kind of scenarios where you find solutions that don't have a continuous new space. So you cannot reach from this point to this point continuously. So this is embedded information that we created maps to explore that and to embed that into the design of manipulators. Not just for the design, but also for the planning part. And you can see this is for the KUKA. So we explore what's the new space information that you have, and also how much the robot flips and where it flips. So there are some flip motions that you can see. Some of the joints need to flip to reach the same potential of new spaces, discontinuous new spaces. So we evaluate that, and we build maps that can be used for the community to understand where the flips happens and where you have more manipulability and more new space capabilities. So how much new continuous new space you have on that spaces. We figured that some of the most common manipulators have different flip solutions. So for instance, let me go directly at the end. The KUKA has 8 flip solutions, where you can see this jump of the joints, while the Franca has 4. And you can explore that information, for instance, while you are doing RT planning. If you have the same flip solution, your robot doesn't need to do that kind of motion behavior that everybody's familiar with RTs. Is basically because it's looking for where it does the flip of the joints, because your different IKs that you use in the joint space, they are discontinuous, so they cannot find a continuous solution for it. Now, in addition to exploring the embodiment of the robot, another important point is exploring the task itself, the understanding of the task. So here we devised some contact-rich manipulation tasks where we are evaluating the data behind that, and model that data different, just getting the data and putting the algorithm where we have the forces, the torques, the velocities of the contact points with the world. We're trying something different. So here we're exploring the relationship between them. So basically you can see in these plots, especially where my mouse is, and I hope you can see it, this is the inner product between the forces and torques, torques and torques, forces and velocities. So basically the relationship between every spatial element of the interaction. That is to say, how much a force affects the torque. So if apply a force, what is the result in the torque? And vice versa. And then we can evaluate with the inner product, which give us the angle between those vectors. So this is basically the inner product between those in a time series. And you can see that for different tasks, they are very clearly different among them. But more interestingly than that is that the inner products, they build this sort of rotation matrix. And because they build this sort of rotation matrix, they lie in the Riemann space. So the next step is to evaluate what kind of Riemann properties we can think of, analyze the distance between this sort of task definition, which allow us to do projection and other kind of tasks as well. And here you can see just the time series, how much different they are. And visually you can identify that. We also use some classifiers, and that's very easy to see and classify those different contact reach tasks just by using the relationship between the elements. All right. So going from these two layers, I'm finally reaching the final layer, which is the human part layer, where you have this higher level abstraction, where you have the collaboration, directly collaboration. So here is a scenario where you have wanted to have some physical, forceful interaction. And you can see, basically you have to model the forces. You have an idea of the maximum forces that you can have, of course, and what your system can support. And you can think about a task, for instance, like a cutting a board, where you can discretize the forces and you can do some IK checks to build up a map where they are connected. So you see where the robot can actually execute those forces. We did that just in a way to minimize, to make the interaction more fluid. So if you analyze all the forces that the robot needs to execute at a given point in space, and you define a manifold where they connect. So basically where a different IK can support different forces, we can build a direct connected graph and evaluate that. So we know what are the minimum required grasps to do a task. We can do the same integrating service. So integrate different kind of contacts, not just the grasping contacts, but also robot grasp, object to surface, and surface an object to the contact points of the robot. And here is just an illustration of what the requirements we have. So if you just have the two grasps and forces applied, you cannot sustain the force. And if you use one grasp and the object environment, you can also support the force. The only way to support it is if you have one grasp and you build one contact point of forces together with the surface. And that allows us to do this kind of complex task without having to redirect and change the whole configuration of the human during the interaction. And this is just an example of showing what the system can do. So basically here, mounting an IKEA chair, and at the same time, doing this regrasping there, where don't need the surface to do the regrasping. But important point that I want to highlight here is that during this collaboration, we are able to do the task, right? We are able to complete the way we wanted. But while I was doing this task, my hand was always in this weird configuration. So I was able physically to complete the task, but it was always very uncomfortable the way I was doing. So I was doing a research, so I was not doing that daily 100 times. But if you want a robot to do that in industry, this naturally would cause injuries in the person. So it was basically what we were doing is just thinking about the task, right? We are not thinking about how safe or comfortable that task is for the human. So we had to rethink about our whole strategy. So think about the modalities that we have from the humans and how we have this teamwork playing around in physical interaction. So naturally, the first way you go is the natural language processing. So how naturally communication plays around with robots. So he is basically carrying a knife around the person, not very nicely. And we can tell the robot just to reduce the speed. The robot should be able to understand that and ground that into robot capabilities to execute that task. The same way, you should have the capability to expand that to different contacts. So if you have a manipulator or if you have a drone, understand that and execute that on real time. So this is basically the model that we used. We can go in a little bit more details about all the topics, but I'm just trying to give this massive overview. We are now including forces in the same context. We can also include gesture and postures, so implicit modalities of communication. So for instance, if you are pushing a box or moving a heavy box, naturally we know how to execute that task. So naturally you know how you should do that. And that's basically because we have model information for that. It's basically how our joint torques generate the forces that are required to perform that task. And that's captured by the manipulabilities. So we have been working on transferring the manipulabilities between human kinematics to robot kinematics, which of course they are different. and also exploring that information in performing different tasks. So just to give an idea is that what I'm talking about is scenarios where the trajectory is, when you're doing learning by demonstration, the trajectory is roughly the same. Is roughly the same, but the posture is completely different, as you can see here. So the posture are rather different, but the trajectories of the object and your hand are the same. So here is, I just wanted to highlight this point while we're executing the task. Here is one handover task, which you're only observing the endpoint. You're not observing the endpoint and the posture of the human. And just having that information, giving just the endpoint information and the posture through manipulabilities from the human to the robot, we see this kind of behaviors where the robot adjusts its postures. And you can see that's the only one that really changed its postures to adapt it to what was demonstrated. And that allows us to do different tasks, even to perform the task properly, while if you don't have that, you will not be able to do that. So going back to our previous experiment where we have the forceful interaction, another modality that is not super explored, but should be, is the human biomechanical information, which is implicit information that I have while I'm manipulating something with another human. So this information should be embedded in the robot. This is a very trivial example when you're cutting a board. So if I'm cutting a board with someone and I know what is the direction of the cut, and this is at the same task, so it's a cut in the longitudinal direction of the board. If I place the board in this first configuration, I know that the person would have to do this task, which is highly uncomfortable. While if I do it in the other way, I know that it's much easier for the person to execute the task. So that's the task that how I would like the person to do it. So this is basically a planning over the biomechanics and musculoskeletal space. So here I have a task definition. I know how the human should execute a task. I explore its biomechanics and all the possible ways it can execute a task. And finally, I design a plan to do it. And this plan is basically one that minimizes the muscle activity, satisfying breast stability, geometric constraints, and biomechanical constraints. Performing that information, did some experiments, and just to highlight, this is in blue is using the optimize method where it minimizes the muscular activity. In gray is the one that uses a random planner. It just takes a random solution that is satisfying just the robot behavior. And in red is the one that we literally ask the user to define how they would like to interact with the robot. And these are so just to highlight, in top left and top right is uncomfortable configurations, and top left and bottom left is the comfortable ones. So here we can see the map of the distribution of the different experiences that we have in the user study. So in blue, you can see the optimized space is much more constrained. So we are literally constrained the person to execute a task in a comfortable space, while the gray one is everywhere because it's random, and the red one is in between. Measuring the muscle activity during those experiments, we realized that by optimizing the muscle activity, we can reduce up to 70% of the muscular energy, which that reflects in less injuries. We also use that to predict the human motion, and we built maps. So basically, you can see that here we evaluated if the humans would always look for places where the manipulability and the muscle activity are better. So this highlights the red area, which is a comfortable one. So we were able to predict some of the motion of the human. The main drawback of this method is that the muscular space is massive. So to reduce that dimensionality, we designed this rapid human manipulability assessment, which pre-computes the whole information, builds up also with ergonomics design, so that is available online, where the user can just look where is the requirements, and you can execute that. So now we are building the second version of that, including more information about forces indexes, dynamic manipulability, and giant limits, in addition to all those related to the biomechanics information of the user. So this will be called the second two version. It's in collaboration with MathWorks, should be ready in a couple of months. I'll just go quick on what is the design behind that and what people are gonna have once you have that ready. So you can do forward kinematics and see the capabilities of the human performing the task, and you can do inverse kinematics and also analyze what are the results in the manipulability space and the biomechanics muscular space you have. Because it's a discrete word, you can also use that for planning, and that's for learning, and that's our idea, to share that to the community for learning. And that's a wrap. And now I think we started a bit. Someone said cannot see the slides. Can everyone see the slides?
Yeah, I can still see the slides.
Oh, okay.
Yeah, I can see it as well.
All right. I mean, I'm wrapping up. So this is just like for me to say that this is the idea behind it. So having this layered approach that allow us to have really strong saved behaviors all the way to natural language and biomechanics embedded, such that a robot can perform those tasks close and safely around humans. And just want to wrap up. Thank you, everyone that worked with me, especially the students that have made the work possible. And if I have any question around the specific topics, if I have been a bit quick in anything, please let me know as well. And we can talk a little bit. I was a bit afraid of going everything because I think that the main point is to highlight the holistic view that we need to have as a robotics community in the topic. So I hope I did that. But if there is any specific question on any specific topic, I'm happy for us to go more in depth on that.
Thanks, Louis, for the wonderful talk. Going like forward in the future, what do you think, Louis? Like, how much of that came from a general perspective? What should be the parts that we should have model? How much of it should be data driven, and what would be the mix? And is it task specific, or it can be very general, end to end? What are your thoughts?
I think I'll always be afraid to say not task specific, although we strive for things that are task agnostic. There are always task conditions, specific task conditions that require a little bit more from one and another. If you have a surgical robotics, I wouldn't like to be operated by something that is fully model free. So I would like to have way more model-based constraints in surgical robotics. But if it's just something for surface or just for animation, that having something more model-free, it's fine. But in the end, I think it's always the solution on and I think that's something that as a community should be looking at, on doing these embeddings. So how we can embed the model-free solution that we get into constrained model-based systems that we can have more guaranteed behavior, certified behavior, legible behaviors, and even explainable behaviors. I think in general, people are going to be looking for more explainability and legibility of the robots, and that requires a little bit more model-based methods. And one thing, a little bit more modularity, so we can play around with them as well. So things that are more modular, that we can understand, it's more appreciated than end-to-end, where we don't know if something fails where it is. And I think we should, as a community, be paying quite a lot of attention on that.
Cool. Thanks. Any other questions?
I had one. Thank you so much, Louis, for the great talk. So I wanted to understand, because I think a lot of the examples that we looked at involved manipulators. And for human-robot interaction, especially with how the advances in industry are moving right now, at least, the kind of embodiments that they're picking seem to kind of replicate a humanoid type of setting. So where do you think we need to be focusing our efforts when it comes to PHRI with respect to embodiments?
That's a good question. I think that we are pushing quite a lot on humanoids, elected humanoids, and I cannot see. I mean, I see the drive behind because it seems natural that, whenever we always hear that it's because the world is built for humans, but quadrupeds, dogs move around in our world quite well, and they are better than two legs most of the time. A little bit more energy consuming, but a little bit better. And we build wheels because wheels are much better than the legs for moving and more energy efficient. So having this argument that the human environment, it's only humanoids are gonna play around, I think that's quite limited. I think we need to think about what we want robots to have, what we want robots to do, and what kind of adaptations from this environment we need to have. Once cars start being a thing, we change the whole cities to adapt for cars. So cars wouldn't allow to move around. The cities were built for people to walk and small horse-driven chariots. And we changed the cities. Not saying that we should change the cities and everything for robots, but we shouldn't be limited to that. And now what morphology, what kind of topology should be thinking? That's a big question. I know there is so much inspiration in nature and amazing works that we see around. I think we should explore those. But in general, I see a boom on soft robotics, and I think there will be quite exciting things coming from there in the next 10 years.
Yeah. Hi, Luis. I have a question. Yeah, great talk.
Yogesh.
And so my question is about like when we plan these contact-rich manipulation tasks, do we consider any contact models during planning phase, or it's mostly like sensor feedback and the algorithm response on the feedback-based control loop?
That's a very good question. So there are different strategies. There, depending on the task that you have, for instance, if you're doing no precise manipulation, the traditional way to do it in the community has always been to use physics engine-driven environments to emulate what kind of behavior you're going to have, just because modeling the friction would be so impossible to a new scenario. So we would try to emulate different kind of conditions and see how that behaves, and start moving and see what kind of behavior you get in your physically driven environments, which now people call digital twin, and try to adapt to that and make the corrections from there. I think having the feedback, it's naturally super important, but having the feed-forward information, especially for the first contact, is very important. I see always a little bit inspiration on the human side on that, because we don't have our manipulation skills. If you see our embodiment, the response that we have from our manipulation to the brain is not 1 millisecond as in robots. It's 100 milliseconds that sometimes takes. And if you use vision, even more. And we're still able to do these amazing manipulation tasks. And mostly because that involves prediction about what we are expecting the systems to be, which allow us to build some intelligent feed-forward models on how to behave. But at the same time, we have this very precise feedback system, which also changes what the feedback and reflex model we have. So it is a little bit of both. I think modeling is the hard part, and getting reliable data is also a little bit hard to have. But in general, having the feedback will be the answer for us to push it forwards. I hope I answered, but I think I was just trying to emphasize that both things are important. I think a good prediction is critical, but during interaction, better models and better feedback is important.
Yeah, makes sense. But yeah, is it considered when we do like drilling and cutting tasks on the Dexter? Are you considering those? Like during planning, what would be the contact forces?
Yeah, so I was not really considering those contact-rich manipulation, but on those cases, it was a little bit easier because in the end, that was the human doing the task of the cutting and drilling, and the robot part was more about the resistance. So the robot should resist to the forces that has been applied. So you just need some upper bounds. You need some what are the limits that the forces are gonna come, the sequential forces are gonna come, and how to adapt to that. So what we were planning over there was that we knew what are roughly the forces the human can apply. We knew what a task requires. So if you have a cutting, what direction and the cone that the forces leads. And if the robot is able to sustain that force on that point, then we know that the robot can perform the task. So that was mostly on that aspect. So it's a little bit easier situation because it doesn't require precision. It doesn't require dexterity. It just requires resistance to the forces given.
Okay, thank you.
Yep.
Thank you, Luis, for the time. It was wonderful having you for the
Thanks
first
so
session.
much.